Welcome to the deep dive. We're getting straight into the research, and today we're diving into sources on a really groundbreaking piece of work from Monash University. It's about next-gen computing.
That's right. We're looking at this incredibly small, fluid-based chip. The amazing thing is, it's designed to act like the brain's neural pathways. And its memory.
Yeah, it's fascinating. Our sources, mainly the paper in Science Advances, they detail how this, well, coin-sized device actually functions.
Yeah.
So our mission today, understand the mechanics and, why this is such a big deal for brain-inspired computing.
Neuromorphic computing, exactly. It bridges material science and computer design in a very physical way.
Before we really unpack that, just a quick word about our sponsor, embersilk.com. They're doing some really innovative work in sustainable silk technologies. Check them out.
Okay, so let's get into this chip. The Monash team used something called a metal organic framework, or MOF.
Yes, MOF. You can sort of picture it as a crystalline material, almost like a sponge, but with incredibly precise nanoscale pores. Right, and the breakthrough is how it works, not like normal chips.
Exactly. No electrons flowing through solid silicon here. Instead, this chip guides ions, things like protons and metal ions, through tiny liquid-filled channels.
So it's computing with fluids,
Yeah.
nanofluidics.
Precisely. It's controlling the traffic of ions in these liquids.
Okay, but here's what's really interesting for you listening. How does something based on liquid actually hold a memory? It's not like a solid-state drive.
Ah, well, that's the clever part. It acts as a kind of nanofluidic memristor.
Memristor,
Yeah.
meaning memory resistor.
Basically, yes. It remembers past voltage changes by physically altering the pathways the ions take. Think of it like slightly pinking a tiny, tiny hose.
Okay.
That change in how easily the ions flow through that kinked path, that is the memory. It's short-term, like the plasticity you see in neurons.
Wow, okay. And you mentioned the structure is key.
Deeply key. It's hierarchical. The MOF has these internal pathways, but they're on very different size scales. This lets it manage different types of ions in completely different ways.
Hang on. How does it differentiate? I mean, you've got tiny protons, just hydrogen bits, really, and then much bigger metal ions, like potassium. How does one material channel them differently? Isn't it just one flow?
Well, that selective control is the breakthrough. They achieve something quite remarkable. They call it unprecedented triode-like nonlinear proton transport.
Triode-like. What does that mean in practice?
Okay, so think of the metal ions, like potassium. They behave more like a simple switch, a diode. Either they flow or they don't, on or off.
Right.
But the protons, the chip can control their flow much more finely, like a dimmer switch, not just on-off. It's a continuous, nonlinear control.
A dimmer switch. Okay, so much more nuanced.
Exactly, and that dimmer switch control over protons allows for those complex memory effects, the gradual changes. It's a type of selective conduction we haven't seen before in nanofluidics.
Got it. So connecting this to the bigger picture then, what could this kind of liquid-based fine-tuned control mean for the computers, that we all use?
Well, it offers a potential way around the miniaturization limits that silicon chips are hitting. The famous Moore's Law slowdown.
Right, the end of shrinks and transistors.
This could open doors to computers that process information more like we do, systems that learn and adapt based on past states, not just calculate predefined steps.
Truly neuromorphic.
That's the long-term vision. It paves the way for advanced fluidic chips that might complement what we have now, or maybe even, eventually, overcome some of silicon's limitations.
So summarizing that, two potential paths forward. One is developing this liquid-based data storage.
Short-term memory, yes.
And the other, maybe the more profound one, is building actual neuromorphic systems, computers that think differently.
That's the hope, yes.
Okay, fascinating stuff. So as you finish listening and go about your day, here's a final thought to chew on. If the very basis of computing starts shifting, moving from solid electronics to, well, flowing ions in liquid, how might that change the actual physical form, the shape, the feel even of the computing devices you interact with every single day? Thanks for joining us for this deep dive.